Welcome to the course on satellite attitude dynamics and controls. So, we will go first to the representation of the satellite in the orbit, how it is oriented, how its orientation is represented. So, let us start here. Okay, so, let us consider that we have the earth here, it can be any planet or natural satellite of that planet, and there is a satellite here in the orbit, this is the orbit, and satellite velocity vector can be represented as v, which is tangential to the orbit. Okay, and radius vector of the satellite, which is from the center of the earth, let us say this point is O, this point is O here. Okay. So, radius vector is up to this point, okay, to the point O from here to here, and this is the radius vector of the satellite from the center of the earth to the point O, which we can say center of mass of the satellite. Okay. So, we are not right now we are not discussing about the dynamics of the system, rather we are just looking into the orientation of the satellite system, how it is oriented in the orbit. Okay. So, it can be a circular orbit, it can be a and it can be an elliptical orbit. So, this direction taking it outward, this generally this called the local vertical LV. Some of the authors or some of the books may tend to represent this the opposite direction, that is toward the center of the earth as the local vertical. So, irrespective of whether you indicate the local vertical either in this direction or either in this direction, it is okay, but you should continue with a particular convention. That is, if you are representing in this direction, you should keep continuing with that, you cannot keep exchanging in between, the whole then the calculation will be wrong. Okay. So, separately representing here, this is the center of the earth, and let us suppose that for simplicity we have the circular orbit here, and in this direction we will assume that this direction is the local vertical. Okay. So, this is our local vertical and we will indicate this as z 0. Z 0 means this is about the orbital frame. Okay. I will explain you in details about all these things. This direction we will indicate as x 0 and y 0, then we can take the right hand rule, because we will be working with a right hand triad. So, taking x to y, this is downward. Okay. So, downward we indicate it by a cross, and at this point we will have y 0. So, we have the coordinate frame here, which is x 0, y 0 is downward into the page, and z 0 is going toward the center of the earth, which we are calling as the local vertical. Okay. Now, just as in the case of the aircraft, those who are aware of the aircraft notation, so the roll motion it is always taken along the velocity vector. So, here in the case of the circular orbit, your x 0 and the velocity vector v of the satellite, they will coincide, because in the circular orbit the velocity vector is tangential to the orbit and also in the elliptical orbit, but here the if you take the elliptical orbit, suppose I have the center of the earth here and satellite is going in some elliptical orbit. Okay. So, my velocity vector will be here in this place, but if I take this to be the z 0 direction, then my x 0 direction will be along this direction. Okay. This is normal to the z 0 and as usual our y 0 will be pointing in downward. So, here v direction is not along the x 0 direction, but here at this place this has the same sense. Okay. And in the aircraft, as you know that the roll axis is taken along the velocity axis. So, in the case of the circular orbit it gets simplified and the roll axis we can take the right hand rule that if this is the velocity vector. So, we can take the right hand rule like this. So, it is a rolling like this. Okay. Then we consider this as a positive roll. Okay. And so, here the velocity vector is along this direction and this is a positive roll. So, I will indicate on the board it like this. This is our the rolling motion. So, what I have indicated here, this is called the x 0, y 0, z 0. This is termed as the orbital x system or the orbital frame, orbital reference frame, and we assume the body axis the body x system to be coinciding with the orbital x system. So, here say in the beginning I am fixing I have say in the case I have this mobile. Okay. So, along this particular axis I fix this one axis along this direction. So, this I call as the x axis, along this direction I fix the y axis as in the case of aircraft, and z axis downward, which is the normal yaw axis in the case of the aircraft. So, following the same notation. So, right in the beginning just assume that x 0 and x body axis they are coinciding. Similarly, the z orbit and z body axis they are coinciding, and similarly y orbit and y body axis both are coinciding. Now, once the satellite is rotated, so right in the beginning they are all coinciding with the orbital axis, all the three body axis they are coinciding with the orbital axis. Now, if I rotate like this, so obviously the z body axis it will no longer remain in the same direction as the z orbital x. Say in the case of the aircraft, as you are taking z to be vertically downward. Now, if I rotate, suppose I fix in the space one line like this, and this we assume that this was the previous orientation of the z body axis. Now, if I rotate it this aircraft, so the perpendicular to this or the z axis of this will rotate from this place to this place. So, this was the original position, now it has gone into this. So, in the case of the this satellite, if I assume z to be here and x 0 is already here, and obviously the x and y and z body axis they are coinciding with the orbital axis. Now, I rotate it by certain angle. So, if I rotate about the y 0 x, which is indicated here, which is the y direction of the orbital x system. Now, it will the x axis will come to this place, means the body x will get displaced from this place to this place, and this is the orbital axis will get this z body axis will get displaced from the z orbital x to this place. And let us say that this angle we have rotated, this is theta, and this angle is also theta, this is theta. Okay. So, the body axis rotation we are representing with respect to this orbital axis. Now, what we will see that as the satellite moves further, okay, it goes from this place to this place. So, the center of mass is located here, a radius vector we will draw from this place to this place. Okay. Now, obviously, you can see that the satellite orientation has changed. If I assume this page, say if I write this as the x and y, and write this as the x inertial axis and this as the y inertial axis. So, you will see that the in this reference frame the satellite orientation is changing. Right now, it is like this, and now it has gone here into this position. Okay. So, the orbit, if we connect the center of the earth and center of the satellite, okay, so this is the new radius vector. So, this is at time t 1. So, this will at time t 2. Okay. So, in this new position, this will be the local vertical, or either inside this will be the local vertical as per our assumption. We are continuing with the local vertical directed inward. Velocity vector will change its direction, it will be here in this place. Okay. So, by going from one place to another place, our orbital x orientation, which is here in this place, let us say this is z 0 we have indicated, and in this direction this is the x 0, and vertically downward this is our y 0. So, with respect to this, here you can see in this place that the orbital x system itself it has rotated. So, this is now x 0 and this is z 0, and vertically downward this is our y 0. So, the orbital x system that is also rotating, and with respect to the orbital x system, body will also be rotating. So, there can be issue like either we want to show the satellite orientation in the inertial frame, or either with respect to the orbital reference frame. And one thing you remember, there is a difference between the orbital this coordinate frame there is difference between the coordinate frame and reference frame. In the coordinate frame, usually we describe the coordinates of a system, like I have a body, say I have a body like this, okay, and I want to describe this coordinates of this corner. So, let us say this is x, y and z vertically up, and if this is a unit cube. So, this will have coordinate 1 1 1. Okay. So, this is coordinate frame, while the reference frame it differs from the coordinate frame in that in the reference frame we describe the motion of the particle, or it may be the motion of a body. Okay. So, basically the reference frame stands for the description with respect to the reference frame. Basically, we are describing the motion of the body or motion of a particle, while with respect to the coordinate frame we describe the position of a particle. Okay. Not necessarily the equation of motion will not enter into that. So, we will make this distinction that coordinate frame, especially this stands for only for the description of location of the particle, while the reference frame it will stand for the describing the motion of the particle. So, for orientation of the particle, it will here in this case orientation of the satellite, it changes from this place to this place, both in the this x y inertial frame and also in the orbital reference frame, which is x 0, y 0 and along this direction z 0. Similarly, here x 0, y 0, z 0, and orbital X system, that itself it is changing its orientation with respect to this inertial reference frame. So, which reference frame we are trying to refer to the orientation of the body, it all depends on the our particular interest, what we are trying to do. So, let us go to the next page. Say I have earth here in this place, and I have a satellite here. On the satellite there is a transponder or it may be a camera. Okay. And this direction as usual we have assumed this to be z 0, this will take as the x 0 direction, okay. And going into the page this will be described as the y 0, and with respect to this we are describing the body X system. So, basically in the case of the aircraft, as you may be aware of, and those who are not aware of, still they can get to this notation that if the body X, what we have represented on the previous page, it rotates with respect to the orbital reference frame. So, the roll axis of the body frame, that will be always indicated by x, that is the this x axis of the body frame, that will act as the roll axis, while the z axis will act as the yaw axis and y axis will act as the pitch axis. This is the most common notation which everybody should follow, because if you look in some other book, if you go to certain reference, then you will find that the same notation is followed, and to maintain a synchronicity between my presentation and whatever will be given in the book or any other reference material, I will follow this notation throughout the text. So, if you are looking for that your camera of the satellite should always point toward the center of the earth, then what is required, that as your satellite moves in the orbit. So, right now it is here, after some time satellite will go here in this position. So, to orient the camera along the new direction of the satellite, see if camera has to point always toward the center of the earth, it may be required from the point of view that I have a on the ground station some object or something kept that I want to scan or send certain signal. Okay. So, I need to point my camera or the transponder all the time here in this direction. So, you can see that my satellite has in the inertial reference frame, it has rotated from this place to this place. So, inertial frame as usual we are indicating here in x y direction or whatever the way you choose. Okay. So, in the plane, this plane you can say this is my x direction, this is my y direction, and from in this reference frame this has changed its orientation, and the body axis as we have indicated, this is x body axis and z body axis we have indicated here and y body axis here. So, if the camera is maintained along the center of the earth all the time, so again your x body axis should be here, z body axis should be here, and x body axis should go here in this direction, and y body axis will be downward, and obviously your x 0 will also be along the x body x and so on. So, what we observe from this place, that depending on our need, okay, orientation with respect to the orbital reference frame or the inertial reference frame can be given. So, here in this case with respect to the orbital reference frame, if you see there is no rotation, but if you look into the inertial reference frame. So, obviously, with respect to the inertial reference frame, this satellite orientation is changing. So, for describing the motion of the satellite, it is very much required that we properly assign notation of the orbital reference frame, the body reference frame and the inertial reference frame. Inertial reference frame, as you are aware of, this is the frame in which Newton's second law is defined. Many of the students, they are not aware of the this fact, as over a period of time I have learned that, but previously I thought that many people may be aware of. Let us discuss about that also little bit, so that you are aware that what the inertial reference frame is. Suppose f equal to m a and we set this quantity to 0. So, this implies a equal to 0 means d square x say or d square r, whatever you are writing, by dt square, this equal to 0. So, this implies dx by dt, this is a constant which is nothing but your turns out to be a velocity and it is a position. Then let us say this constant you are writing as b. So, this is a vector. So, b t and plus another constant c. So, position of the particle it is a changing if the acceleration is 0. So, and if suppose b is 0, so then this becomes c, x equal to c, and c is a constant. Okay. So, this simply implies that particle is remaining in the same place if there is no initial velocity. And another way, this tells that this states about the Newton's first law, which tells that until unless a particle is applied or on a particle, until unless you exert an external force, it will not change its position, it will try to remain in the same position. Then the question arises, why do we need the first law then, if the second law itself states. So, this is not the thing. The thing is that the second law is defined in the inertial reference frame. So, this is defined in the inertial frame. So, second law we are defining in the inertial frame, and first law, this is the definition of inertial frame. So, this defines an inertial frame. Now, what we can see that not only this information is vital, because we always define the work out with the Newton's this second law in an inertial frame itself, and whose definition is given by the first law, which defines the inertial reference frame. Now, beside this, in the first law also there is inherent that because of the mass of the system, the mass gives inertia to the system, because of that it tries to remain in the same position. The greater the mass, the greater the force will be required to change its position, but books they do not define it, and moreover you should be aware that the Newton's contribution was only the third law. The first two, the first law and the second law, they were already existing in the literature before Newton. So, in this view, we see that in inertial frame we can describe the orientation of the body, or with respect to the this orbital reference frame, with respect to the orbital reference frame itself, we can describe the orientation of the body. Say, so, coming to this place, here in this place your it may happen that instead of you have the x 0 direction here, z 0 in this direction, and y 0 here in this direction. Okay. So, instead of this direction, your of x b and y b, your x b may be looking something like this. This is the x b and this is the z b, and y b remains along the same direction. Means your with respect to the orbital reference frame, your satellite has changed its orientation. So, this is a very simple representation here, that we have rotated about the y orbital axis here in this case. So, rotating about the y orbital axis, the body orientation has changed to x b, y b and z b, and y b is directly going inside. So, this is the rotation about the y b axis. In general, this rotation may be much more complicated, and rotation can take place also about the x b x, z b x and y b x, all the three axis rotation can take place. So, I have a body here, okay, and this is the x body axis, this is the y body axis, and downward this is the z body axis. So, I can rotate the body about the z axis, I can rotate the body about the x axis, okay. I can rotate the body about its y axis. So, as I am rotating, so then body is also this z body, you see here in this case, if I am rotating about the y body x. So, this z body x is also going up. So, we have to become conversant with this notation of the different reference frame with respect to which we are going to describe the equation of motion. So, coming to our conclusion, in this why do we require different reference frame? The first one is that we need to orient the satellite in the space itself. It may be required that, say, here it may be case that in this inertial reference frame, your satellite should always point along this direction. It should be always like this. Okay. It is coming from this place to this place in the orbit. So, it should go like this, and this may be case here, this may be case related to, say, the Hubble telescope. You are pointing towards particular star. So, star are at many light years away from us. So, almost the light coming from the star to us, it will be assumed to be parallel. So, basically in that case, you have your satellite here and you have your satellite here, it is a pointing toward the star all the time. So, in this case, your satellite is undergoing purely a rotational motion in the inertial reference, purely a translational motion in the inertial reference frame. That you can check from this place, that if I have say a pin here, and two rods are hanging, and if I attach a body here and there is also a pin, okay. If I push it, so this will get pushed only in this way. Okay. So, it will come from this place to this place like this. This is purely a translational motion. On the other hand, if I have a body like this, okay, it is attached here. Here it can rotate, but here it is a fixed. Okay. There is no rotation involved here. So, here I am fixing. So, as you rotate about this, so suppose along this direction. So, it goes from this place to this place and it looks like this. So, you can see that here in this case, this line, these two lines which were like this, now they have changed here its orientation. While in this case, if I have one line here or this line, these three lines, so they are not changing their orientation, they are remaining in the toward the same direction. Okay. So, this is purely translational motion, while this is purely rotational motion. So, there can be combination of rotation and translation, which happens in the case of the satellite, in the case of the aircraft. So, here if you are pointing it inertially, then it is a purely translational motion, while you are trying to point toward the center of the earth, then there is a rotation involved. As you can see that this is rotating from this place to this place, its orientation has changed, and also the translation motion is involved, because this coordinate and this coordinate in the inertial frame, they are different. So, the translation has taken place from this place to this place, and also the rotation has taken place, where this line, it has changed its orientation to this line. So, we conclude this introductory chapter which is related to the representation of orientation of the satellite in the orbit. And next time in the next class, in the next lecture, we will go with how to present the orientation of the satellite in the orbit, that we will learn. And slowly we will build up, and once we are aware of the orientation of the aware of orientation, how to represent the orientation of any object in space, or with respect to any coordinate frame, or with respect to the any reference frame, then of course, its rotational motion also we can describe. So, without considering the torque acting on the system or the force acting on the system, once we describe the motion of the particle or a rigid body, it is called the kinematics, and beyond that we go. So, where the force is involved, so that part we call as the dynamics, where the force or the torque is involved. So, first we will look into the rotation of the body, then we will go to the kinematics of rotation, and thereafter we will start with the dynamics, which is our final objective, learning how to manage the satellite in the space, how to orient it, how to control it, so that it can serve my purpose by say pointing toward the certain star, the Hubble telescope. So, that is one objective, it should do in a very precise manner, some milli of arc second or the arc second accuracy if you require. So, it is a very precise control, it is you have to do, and for those kind of precise control you need the precise controller also. Precise controller means the controller, suppose on the earth you put a small jet on its surface. So, tangentially to the surface. So, it can rotate the earth, but earth is such heavy that it will its mass is so big that even if you apply substantial force through that jet, it will hardly it affects the earth. So, depends on the size of the body, how much accuracy you require, and accordingly you have to choose the propulsive system or the torquing system, which will meet your objective that you are planning for certain mission. Okay, thank you.